And now we will generalize PCA with the singular value decomposition. Well, the observation that it is a generalization can be an interpretation, and as you know, I'm only telling you facts and no interpretation, so the interpretation is on your side. But we will see, actually, I will interpret it for you in every reasonable conspiracy podcast. Of course, there is an interpretation, even though they tell you they're not interpreting for you, but you have to do it on your own. I'll do it, of course, for you. So we will see that SVD, singular value decomposition, is a generalization. So we're starting actually off here with PCA. So having another look at PCA. PCA is an eigenvalue decomposition of the covariance matrix, which is of dimension d times d. So d is the number of dimensions in the original data set. Yeah? And the covariance matrix can be obtained from the normalized data matrix D by simply computing D transpose times D. Okay, so and well, if the data is not normalized, then you can use the correlation matrix more or less analogously, but with the covariance matrix it's easier. So the covariance matrix is decomposed, as we said before. Eigenvalue decomposition means we have two matrices actually, so V and E. V contains the principal components, so it is a D times D matrix because each column is a D-dimensional eigenvector, the D-dimensional new unit vector in our new coordinate system. Yeah, so this is a D times D matrix. The columns are pairwise independent unit vectors by design, the eigenvectors. And the middle vector matrix here is the matrix that contains the eigenvalues in order to have a defined matrix multiplication here. It needs to be a D times D matrix too, so but it just contains the D eigenvalues, so in that case it's a D times D diagonal matrix. That means all the entries here and up here and below here are 0, just the diagonal entries are set, and so we only have these D entries here, which correspond to the variance along the principal component. So this one here, the first eigenvector, is the variance along the first principal component, and the second one, the second eigenvalue, is the variance along the second eigenvector, and so on, as we are already acquainted to. Okay, yeah, and the decomposition can be found easily by typically numerical algorithms like we have seen before, where we try to come up with the first principal component, then search for the second one, and so on and so on. It's just a maximization problem with side constraints, so numerical algorithms typically do the job quite good. So now, taking a step further, as I told you before, SVD is a generalization. So let's come to the point later why it's a generalization. So first of all, what is SVD? Well, SVD does not work on the covariance matrix, but it works directly on the data matrix. And the data matrix is, of course, an n times d matrix. So d again is the number of features, the dimensionality of the data, and n is the number of objects. I'm sorry for being a little inconsistent, because in the previous sections we had sometimes n as the number of features. Now we have d. D is the number of features and n is the number of objects. So if you consider your data matrix to be just a matrix or a table, then D is the number of columns and n is the number of rows. Yeah. Okay, so we have this data matrix n times d, and in this data matrix we have a number of independent rows and columns, row column pairs or tuples, and this number is k. Yeah, that is the rank of this data matrix. Yeah, the rank k is the maximum number of independent row columns, column pairs or combinations. Yeah, and if we have that, given these assumptions, well, it's not assumptions, but we have the data matrix and the rank of the data matrix, we can this has always a rank, so always this k is always existing, so we can in the worst case, before I start. In the worst case, k is n. Yeah, so we can decompose the data matrix into 3 matrices now. It looks like this one here, O times S times A transposed, and the matrices actually look like this one here. So have a closer look at O. O must be n times something actually, because otherwise it doesn't pay off. So actually it's n times the rank k, and the entries are, well, the matrix is column orthonormal, so all the columns are orthonormal to each other. Yeah, so each of its columns is a unit vector, and the dot product of any 2 columns is 0, meaning they are orthogonal to each other, and they are normalized between 1 and 0, so to say. Yeah, so they are unit vectors. All the columns are unit vectors of O. Then we have S, which need to be k times something, because otherwise it cannot be multiplied with O. So it's k times k. Yeah, so it's the dimension is dependent on the rank of the original data matrix, k times k. And it is actually a diagonal matrix, as you can see here. So like the eigenvalue matrix, so all the entries up here and up there, down here, are 0, and just the diagonal is filled with values typically less than other than 0, not equal to 0. Yeah, k values here. And then finally we have A transpose. So A, not the transposed version, first of all, A is a k times d matrix, and so it needs to be k in order to be multiplied with S, and d, so that the whole multiplication ends up in n times d, which is the data matrix actually. Yeah, so A is again a column orthonormal matrix, but we use it as in the transposed way, in the transposed form. So now the rows are orthonormal. Just keep that in mind. Yeah, it's not the columns here that are orthonormal, but it's the rows that are orthonormal in that case. Yeah, good. So yeah, what does these matrices give you actually? What kind of information do they give you? Well, we won't go into details, but just to grab the intuition, we look at an example. So here it is, the first example. Now let's look at some very specific D. This one is the data set here, the data matrix D. We have the features which correspond to movies, and the objects, the observations, correspond to users, and we see the ratings of users for films, yeah, or movie ratings by users. Okay, and we also see that we have one, so to say, concept, yeah, one independent row column combination, and another one. So the rank of the data matrix is k, is 2, and we see the decomposition of, here is the data matrix again. This one here is here, and this actually would be the singular value decomposition, and we see that the rank here is actually, as I told you, 2, so we have 2 concepts. So the dimension of S is 2 times 2, and the O is then, so how many objects do we have? 1, 2, 3, 4, 5, 6, 7 users, so 7 times 2, and we have 5 movies, so this one is 2 times 5 transposed. Yeah? Okay, and what exactly now do these matrices show? Well, S shows basically that there are 2 concepts. Well, the 2 concepts can be seen here in the data matrix because it's 2-dimensional. It's easy to see here. So we seem to have one concept which is related to science fiction movies, and we have another concept which seems to be related to romance. Don't look at the gender of these things here. They are gender independent, of course. So I'm just telling you facts. I'm not interpreting here anything. But anyway, we have these two concepts: science fiction movies and romance movies. Yeah, and they are visible in S, and S also shows the strength, the energy, the support of these concepts. So the first concept, which is probably science fiction, is supported by more people, more users, more objects, and also more features. And the second concept is a little weaker, but still quite strong. So this one here, a little less many users, and also one less feature. Yeah, but still both are quite strong, meaning that they are very consistent also. Yeah. Okay, so these are the concepts, and the concepts, and A, by the way, relates the movies to the concepts. Yeah, so this is the concept. We have two concepts, 2 times D. So this is the relation to the features, and this is the O is the relationship between the concepts and the users, so the observations in that case. Yeah, so you see here the first 4 users have something to do with the first concept, and the last 3 users have something to do with the second concept. And here the first 3 features have something to do with the first concept, and so on and so on. Yeah, so this is actually the interpretation of this picture, and so SVD obviously gives you a little bit more than just dimensionality reduction. It seems to be like kind of clustering mechanism, but yeah, be a little bit careful here, because typically the situation doesn't look so nice as here, but it looks a little bit more noisy. And yeah, we will have a look at a second example on the next slide, where we see what happens if the data is a little bit more noisy than this one here. That's this example here, second example. Now a slightly different data set, which is a little bit more noisy. So here you have the same concepts, same 2 concepts as before, but we have a little bit more noise here, which is actually this value of Jill here, which well, Jill seems to like or not dislike alien also, and Jane the same. Yeah. So now the support vector machine, yeah, the singular value decomposition looks like this one here. Yeah, so pretty much the same as before in the singular values, but now we have a third concept. Yeah, and still we have these 2 concepts of science fiction and romance, but we have a third concept which is somehow in between. It's not too clear what it is. Yeah, and you see again here the impact of the concepts and or the relationship between the concepts and the dimensions, and also the relationship between the concepts and the observations, the feature, the users in that case. Yeah. So keep in mind, or a summary, the dimension of S, so the K, shows the number of independent concepts in the data matrix, and also S shows the strength of each context. So these actually, the S values here are called the singular values, and they somehow can be interpreted as the strength, the support of each concept. Yeah, and you see here the third one, which is something strange here. The support is very small. The other 2 remain more or less the same. Yeah, they remain actually the same. I think they are not exactly the same numbers as here, but it's just because we truncated at the first decimal position here. Yeah.